All right, here we go. So remember yesterday, we're writing some things down. Remember yesterday we drew the Lewis dot diagrams for the diatomics? Do you remember what they are? You should. Okay, we had hydrogen. It looked like this. We had chlorine, fluorine, bromine, and iodine, and they all looked the same. They looked like this. Then we had oxygen. What does oxygen have? Has a double covalent bond. Very good. And we had nitrogen, which had a triple covalent bond. Let's draw it with dots. Boop, 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 boop. And it looked like that. Okay? These two lines are 4 electrons. These 3 lines are 6 electrons. You should know that. I think that's as far as we got. Did we draw water? Yeah. Okay. So water looked like this, where you had H and O and H, and we had the dots up here. Okay. Did we draw ammonia? Okay, so we got ammonia. Looks like this. We didn't talk about the shapes, that I can tell you. We did CH4. We should have done CH4. What about CF4? No? Okay. Carbon has 4 valence electrons. Each hydrogen has 1. It's going to come in. They're going to sit right here to complete the shells of each one of them. That is going to be CH4, or methane. That's the common name for this. I asked you to start looking at that Ed puzzle that I put up there, where it's naming covalent compounds. The name of this would be carbon tetra for 4 hydride. Carbon tetrahydride. And this one would be carbon tetra fluoride. Because you've got 4 fluorines around 1 carbon. So when we're naming covalent compounds, you are going to name them with the prefixes. What I mean by prefixes, I'm talking about mono, di, tri, tetra, penta, hexa, hepta, octa, nona. Okay, 1 through 9, and then deca would be 10. So if you get something that looks like this, CO2, how do we name that? Carbon dioxide. If the first element, there's only one of it, you don't have to say mono. So you don't have to say monocarbon dioxide. You just say carbon dioxide. Okay, did we draw carbon dioxide? Okay, put a star on this one. Memorize this. Okay, carbon goes in the middle. Carbon has 4 valence electrons. You've got oxygen. Oxygen has 6 valence electrons. Oh, let's not put it there. Let's put it on the side. It's easier to see. Thank you. Okay, I'm going to put an oxygen here. Oxygen has 6 valence electrons. Okay? These X's are the valence electrons for oxygen. Did they let you have lunch? Yeah. Oh, good. All right. Then we got another oxygen over here. Okay. You see how there's an electron that's not bonded over here, and there's another electron up here that's not bonded, and then you've got one here and one here? What's going to happen, because they haven't completed their octets, is just like in the oxygen and the nitrogen, these electrons are going to navigate their way in, and they're going to form double bonds between the carbon and the oxygen. And here we're going to have a double bond between this carbon and this oxygen. So carbon dioxide, move that up just a little bit, actually has two double covalent bonds. Double covalent bond here and double covalent bond there. Two double covalent bonds. Memorize this. Go.
Is there a way to know if somebody has a double covalent bond without having to draw out the entire reaction?
Not really. Okay? There is a set of rules. When we get into more complicated ones, there's a set of rules. I'm not giving you that set of rules just because it might send some people over the edge. So, carbon dioxide, these are the ones they're going to ask you to draw. All your diatomics. That's H, Cl, Br, F2, I did Cl already, what did I forget? I, and then O and N. Okay, those are all your diatomics. You have to know how to draw all of them. Then you're going to need to know how to draw water, CH4, NH4. We didn't get to this one yet. This is ammonium. You need to know CCl4 or CF4, ammonia, NH3, and carbon dioxide. Okay, those are really the ones that show up most of the time. A couple of years ago, 2 years ago, I sat right here and I was talking to my class and I said, does everybody know how to draw water? Yeah, we know how to draw water. And what shows up on the Regents exam? How to draw water. Do you know that there is at least 15 people that could not draw water? I'm going to draw water from now until June. Please know how to draw a water molecule. The O is in the middle. You've got 2 hydrogens coming off of it, and you've got 4 electrons. These are called non-bonding pairs. The easiest way is just to remember what water looks like. Okay? These are bonds. This is a single covalent bond. If I had to put money down on something, you're going to have to draw water or you're going to have to draw carbon dioxide on the Regents. That's my guess. We haven't seen carbon dioxide in a couple of years, so it's probably going to show up. Okay? All right, let's talk about the shapes. The hydrogen is only 2 atoms. 2 atoms in a row is called a linear molecule. My model kits here. You get to play with these next week. All right. So let's say we have 2 oxygens. They're in a row. It's a straight line. Just like that. That's a linear molecule. Doesn't matter what they are. They could be H and Cl. You would have H with 1 valence electron. Cl has 7 valence electrons. That hydrogen's going to come in. It's going to bond right here. You're going to have an H and a Cl. H bonded to a Cl. Okay, it's a linear molecule. They're in a straight line. The next shape is going to be the water molecule. There's your water molecule. Okay, see how they're no longer in a straight line? The reason why they are not in a straight line is because these non-bonding pairs of electrons, this non-bonding pair right here and this non-bonding pair right here, are taking up room. They are pushing these 2 hydrogens next to each other. So what they're doing hate when these little sticks get caught. Let's see if I can get one apart. So let's pretend this is a water molecule. There's a non-bonding pair of electrons right here, and there's a non-bonding pair of electrons right here. It's harder to see on this little model. Let's pull up this thing, and this will show you. Remove everything. This is the oxygen. See this purple one right here? Let's put two atoms on the outside, hydrogen and hydrogen. See how it looks like it should be a straight line? However, when I put a lone pair, a non-bonding pair on there, do you see what that non-bonding pair just did to it? It pushed them out of the way. Okay? So this is a non-bonding pair, and this is a non-bonding pair. And what happened is these two guys are being pushed away by these non-bonding pairs of electrons. So we get something that looks like this. That's why water is not a linear molecule. It's because it has these non-bonding pairs of electrons on them. Easier to see than this. Okay. So this shape that we have here is called bent. Water molecules are bent. They have, come here you, they have a shape that goes like this. Okay, it is a bent molecular geometry. The electron geometry is tetrahedral, but the molecular geometry is bent. And the difference is that electron geometry has 4 spots. There's 4 spots where you're going to find electrons. That's tetra. Bent, there's only 2. You're not looking at the non-bonding pairs of electrons out here. All right, let's look at the next one. The next one's going to be ammonia. Ammonia, NH3, is going to look like this. Nitrogen with 3 hydrogens on it. And that nitrogen has a pair of electrons up there. So if we go back to this, let's build it. Okay, remove everything. We've got 3 on there. However, if you look at nitrogen, do you see how you have this non-bonding pair of electrons here? What do you think that non-bonding pair of electrons is going to do? Push them all out of the way. You see how that they went down? Can you see that? See how they're all facing down a little bit? Because that non-bonding pair of electrons is still taking up room up here. Even though you can't see it, it's there. It's pushing all of these hydrogens down. So really, it's looking like this. Hydrogen, hydrogen, hydrogen. Okay? That would look like, I know they're not the same size sticks, but something like that. Thanks, Trinity. Okay? What shape does this look like to you? Look at the yellow. A triangle. Good. This is called a trigonal molecule. It's trigonal because it looks like a triangle. Let me get rid of this and I'll show you what I mean. See the triangle? 1, 2, 3. Okay. See how it says trigonal? Now there's 2 different kinds of trigonal. There's trigonal pyramid, which this one is. It's a pyramid because this non-bonding pair of electrons up here pushing all of these hydrogens down. If I do this and I don't have that extra pair of electrons on there, let's say I didn't have, this one doesn't have 8 electrons around its central atom. This one is trigonal planar. They're all in the same spot. Now, The Regents does not distinguish between trigonal planar and trigonal pyramid. It just says trigonal. You don't have to worry about having that extra set of electrons. So ammonia is going to be trigonal. If you have an element, like let's say SF3, and you have 3 around a central atom and 3 around it, it's going to be trigonal. Try 3 things around it. Okay, so we had bent, we had linear, and now the last one. Carbon with 4 around it. Hydrogen, 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 and hydrogen. Let's build it. 1, 2, 3, 4. Okay, take a look at that. Does it look like a jack like you played with when you were a kid? You never played jacks before? Deprived childhood. Okay? That's like a jack. They're all 3-dimensionally spread out as far as they can get from one another. Okay? I hope you can see that. Now you've got 4 things around a central atom. The name of that shape is tetrahedral. Tetra, meaning 4, hedral around a central atom. It's tetrahedral in shape. So CH4 or CF4 or CCl4 or NH4 positive, those are all tetrahedral in shape. They have 4 things around a central atom. Linear, they're in a straight line. Bent is a water molecule. It's bent because there's extra electrons pushing those hydrogens towards each other. You've got trigonal, where you have 3 things around a central atom, and tetrahedral, where you have 4 things around a central atom. Now let's look at carbon dioxide. I don't know if we can build carbon dioxide on here. Oh, you know what? I bet you can. I bet you have to go here. Okay? What shape is this? It is linear. Why is this linear where water was not? There's water. Here's carbon dioxide. Why is this one linear and this one's bent? Where they look like they should be the same. There's no lone pairs. So for carbon dioxide, there's no extra electrons on this central atom pushing these 2 oxygens down. And because there's no lone pairs, this is a linear molecule. So carbon dioxide, which looks like this, is also linear. What time do we end? Okay, I got time to do one more thing. All right, any questions on the shapes? Okay. Let's look at water one more time. Again, I'm going to draw water about 60,000 times before the end of the year. Please know how to draw it. Right here in this single covalent bond, I'm going to ask you, there's 2 electrons there, right? There's an electron and one came from the hydrogen, one came from the oxygen. Those electrons that are right there, they're being fought over by the oxygen and the hydrogen. Are they being shared equally or unequally? Unequally. How do you know they're being shared unequally? They have different electronegativities. Okay, so oxygen has an electronegativity of 3.4 and hydrogen has an electronegativity of 2.2. This is 3.4. Okay, who's getting a bigger share of those electrons? oxygen. So these electrons right here are just a tiny bit closer to the oxygen than they are to the hydrogen. Just a tiny bit. Not enough for it to pull the electron away from hydrogen. They're still sharing them, okay? But they're a little bit closer to the oxygen than they are to the hydrogen. I know that they are not pulling it away because the electronegativity difference is still less than 1.7. It'd have to be bigger than 1.7 for oxygen to be strong enough to pull it all the way away from hydrogen. Okay, if that's the case, then this oxygen is just a little itty bitty bit more negative than this hydrogen is. Can we agree to that? Because the electrons are closer to the oxygen than they are to the hydrogen. The same thing's happening here. These electrons that are right here, there's an X and there's an O, are just a tiny bit closer to the O than they are to the H, which means that this is going to be slightly negative compared to this. Okay? This bond, the single covalent bond, the electron distribution between that is not the same. It is not a symmetrical, listen to my words, distribution of charge. Do you know what symmetry is? Yeah. Okay? If it was symmetric, then it would be exactly in the middle. But because the electron is slowly or just a little bit closer to the O, it's not symmetric anymore. It's asymmetric. And because it is asymmetric, that bond, that single covalent bond right there, is what we call polar. It's polar because it has one side that is slightly negative and one side that is slightly positive. That is called a polar single covalent bond. This is also a polar single covalent bond. Now, to contrast that, what about if I had H and H? Where are those electrons going to be? Are they sharing them equally or unequally? They're equally. So those electrons are right smack dab in the middle. Because they are right smack dab in the middle, that is called a nonpolar. There's no side of this bond that is more positive or more negative than the other side. So this is a nonpolar single covalent bond. Polar, if they're not sharing them, they're asymmetric. Oxygen and hydrogen, they're not the same on both sides. Here, they're symmetric, so it is going to be a nonpolar covalent bond. Now, we have a little way of remembering this. That's SNAP. Let's write that down. Symmetric is nonpolar. Asymmetric is polar. Let's get a highlighter so we can highlight. S-N-A-P. SNAP. If it's symmetric, it's going to be nonpolar. If it's asymmetric, it's going to be polar. Look at this bond right here. Is that bond symmetric or asymmetric? Yes, because they're going to have this. Symmetric would be like, let's do any of the diatomics are going to be symmetric. Okay? If I had carbon going to carbon, that's also symmetric. All right, look at this molecule that I'm drawing here. Okay? If I look at that molecule, Each one of these lines is a bond. Let's take this bond right here. Is that a symmetric distribution of charge? Yes, because it's between C and C. If I highlight this bond right here, is that a symmetric distribution of charge? No. So this bond is nonpolar. These bonds are polar. Each one of these bonds is polar. This is the only nonpolar one. Okay? See the difference? Symmetric is going to be the same on both sides. It's nonpolar. Symmetric, nonpolar. Asymmetric, different. Okay? And how do you know which side of that asymmetric distribution of charge is more negative? The one that is higher in electronegativity is going to be the negative one, because it's the one that's pulling the electrons closer to it. So if I look at water again, I know that we're kind of like going, water, you're going to get sick of seeing water. Okay? This bond right here, that bond is asymmetric. It's different. Which side of that bond is negative and which side is positive? The oxygen is the negative side, and the hydrogen is the positive side. And then this bond, it's the same bond, same thing, right? The hydrogen's going to be the positive side, and the oxygen's going to be the negative side. So it's got two polar bonds within that molecule. Now, I know that they left already, but this is going towards where we are. This molecule has a side that's positive and a side that's negative. You see that? Is that molecule polar or nonpolar? Does it have a positive pole and a negative pole? Yes. So the whole molecule is also polar because it has a positive side and a negative side. All right? So you have to watch the vocabulary that I'm going to start using. I'm going to say, is the bond polar or nonpolar? If the bond is different, we're only talking about that one little section, the bond. That bond is polar. This bond is polar. And the whole molecule is polar. Look at this molecule. What's that bond right there? Polar or nonpolar? Polar. This bond is polar. This bond is polar. This bond is polar. Okay? The C and the H, which one's going to get the bigger negative charge? The C. And the H is going to be slightly positive. Do you see that? Okay? Does this molecule have a side that's positive and a side that's negative? No. So the molecule, the whole thing, is going to be nonpolar. Wow. Talk about teaching to the bell. All right, I'll see you on Tuesday, my friends.
Is it bad that I'm already getting tired of seeing water?
Yeah, well, you're going to see a lot of water. A lot of water. How do I get out of this thing? Help, I'm stuck. Okay. All right, so Cordelia's out today. Cordelia, hope you watch this. And Michelle's out today. Who else is out today? We know Rob's back. Kevin, watch this video. Kevin's in Costa Rica? Really? Oh, good for him. All right. Hope you're watching the video. We miss you.